Different forms of Planck's law. In this video, we deal with the different forms of Planck's law of radiation and how they relate to each other. So let's get started. Planck's law of radiation describes the radiation emitted by blackbodies. However, there are different forms of representation. Mainly these differences are due to the different quantities with which the radiation is described, for example the spectral intensity, or spectral flux, or the spectral energy density. Furthermore, these quantities can be considered as a function of either the wavelength or the frequency. We will explain these formulas in more detail in the following. Distribution of spectral intensity as a function of wavelength. The diagram shows the spectral intensity of the emitted radiation of a blackbody as a function of wavelength for different temperatures. The mathematical description of these curves has already been discussed in more detail in the video on Planck's law. We discuss the physical interpretation of these curves in the following. First, we clarify the term intensity. In the physical sense, intensity means a surface power density. The intensity thus indicates the total radiant power of the blackbody, which it emits per unit area. The area is the surface of the blackbody from which the radiation is emitted. However, such a general indication of the intensity does not allow any statement about the extent to which the emitted radiation contains short or long wavelengths. A blackbody emits radiation with different wavelengths. Depending on the temperature, certain wavelength ranges radiate with higher intensity than others. The higher the temperature, the stronger the shorter wavelengths in the emitted spectrum. To investigate this experimentally in more detail, the entire wavelength spectrum must first be divided into many small intervals. This can be achieved in a simple way with the help of filters. The respective filters allow radiation to pass only within a certain wavelength interval. The intensity with which the respective wavelength ranges are emitted by the blackbody can be measured with a detector. In this way, one can now make a statement as to which wavelength ranges are present with higher and which with lower intensity in the emitted spectrum. In this case, however, the measured intensity still depends decisively on the width of the chosen wavelength interval. In simple terms, this means that if you choose a wavelength interval that is twice as large, then twice as many wavelengths will pass through the filter and consequently twice as much intensity will be measured. The intensity measured within a wavelength interval is therefore proportional to the wavelength interval itself. Strictly speaking, this proportionality only applies to very small intervals. However, this also means that if one relates the intensity to an infinitesimal wavelength interval, one obtains a constant quantity independent of the interval width. This quantity is then called spectral intensity. The previously shown diagram shows exactly this spectral intensity as a function of wavelength. The mathematical description of these curves is called Planck's law of radiation. In this function, h denotes Planck's constant, c the speed of light, kb the Boltzmann constant, and T the thermodynamic temperature. In this form of representation, the area under the curve corresponds to the radiated intensity in the wavelength range under consideration. Consequently, the total radiated intensity corresponds to the area under the entire curve. Stefan-Boltzmann law. In the following, we would like to determine the total radiated power of a blackbody at a given temperature. To do this, we use Planck's law of radiation. To first determine the total intensity, the spectral intensity must be integrated with respect to the entire wavelength spectrum from 0 to infinity, as mentioned earlier. This total intensity refers to the radiated power per unit area. The total radiant power of the blackbody is finally obtained by integrating the intensity over the entire surface of the blackbody. If the blackbody emits radiation that is evenly distributed over its surface, a so-called isotropic blackbody, the intensity is identical at every point on the surface. In this case, the total radiated power is simply the product of intensity and surface area of the blackbody. The solution of the integrals finally leads to the Stefan-Boltzmann law, which describes the radiation power of a body as a function of its temperature. The constants marked in red form a new constant, the so-called Stefan-Boltzmann constant. In the linked video you will find more information especially about the solution of the given integrals. The Stefan-Boltzmann law states that the radiant power of an isotropic blackbody is proportional to the fourth power of the temperature and directly proportional to the surface area. Distribution of spectral intensity as a function of frequency. Since wavelength and frequency are related by the speed of propagation, which in this case is the speed of light, Planck's law of radiation can also be expressed as a function of frequency. However, the wavelength must not simply be replaced by the quotient of speed and frequency. This has to do with the fact that the spectral intensity is a quantity related to a wavelength interval. Therefore, one also has to convert the wavelength intervals d lambda into corresponding frequency intervals df. Only the radiated intensities are really comparable, but not the spectral intensities. This means that the intensity in a wavelength range d lambda must be equal to the intensity in the corresponding frequency range df. The emitted intensity di, in a wavelength range between lambda and lambda plus d lambda, is calculated by the product of the spectral intensity and the wavelength interval d lambda. So basically we calculate the area under the curve in the wavelength interval d lambda. Note that equation 2 ultimately results directly from the definition of spectral intensity as the quotient of intensity and wavelength interval. Now we have to assign a corresponding frequency interval df to the wavelength interval d lambda in equation 3. This is done by deriving the function lambda equals c divided by f with respect to the variable f. The negative sign in this equation merely expresses that an increase in frequency results in a decrease in wavelength. At this point, however, only the absolute values of the intervals are relevant, so that the negative sign can be omitted. Putting the relationships at hand into equation 3, the intensity can be expressed in terms of the frequency, and the frequency interval is shown. Equation 4 can be simplified a little bit, and we finally obtain equation 6. If we now divide this equation 6 by the frequency interval df, we ultimately obtain the radiated intensity related to the frequency interval. This just corresponds to the definition of the spectral intensity, this time, however, not related to a wavelength interval, but to a frequency interval. In this way, we obtain Planck's law of radiation in the frequency form. If we compare this frequency form with the wavelength form, we can see the given relationship between the two formulas. Note that when it comes to spectral intensity, it is no longer possible to simply convert the wavelength to a frequency by the formula f equals c divided by lambda. This is because wavelength and frequency behave reciprocally. Both quantities are therefore based on different interval widths. This also plays a role in Wien's displacement law, which we discuss in more detail in another video. Distribution of the specific spectral intensity, spectral flux. To experimentally determine the emitted spectral intensity of a surface element of a black body, the emitted radiation within a considered wavelength interval would have to be measured with a detector. In the video on blackbody radiation, the realization of a blackbody by means of an opening leading into a cavity has already been described in detail. In this case, the surface element to be examined would correspond to the area of the opening, which completely absorbs incident radiation and thereby emits blackbody radiation itself, also called cavity radiation. The radiation propagates spherically into the half-space. For the measurement of the emitted radiant power, however, it is not sufficient to place the detector somewhere in a fixed position where only a part of the radiation is detected. One has to detect the radiation around the whole half-space to actually measure the total radiant power. However, the radiant power of the surface element, this means the area of the opening, is not the same in all directions. Thus, one cannot assume that the power measured with the detector at one place is the same at another place. Everyday experience already shows that the radiant power of a flat surface element is dependent on direction. Imagine a large glowing metal plate. If you look at this plate frontally, you will perceive a relatively strong thermal radiation. This thermal radiation is part of blackbody radiation. The radiant power is therefore relatively high when looking at the plate from the front. If you look at the glowing plate from the side, however, the thermal radiation appears less intense. This means that the radiant power is lower. This can be explained by the fact that the plate appears much smaller when viewed from the side, and thus has a less effective radiating surface. This situation can now be transferred to the opening of the cavity, which, as a black body, also has a flat radiating surface and, depending on the viewing direction, appears to be of different size and thus radiates with different intensity. Obviously, the area appearing in the viewing direction, the so-called projected area, has an influence on the perceived or measured radiant power. The projected area can be clearly illustrated by imagining the detector as a flashlight. The shadow that the illuminated surface element then creates on a screen placed behind it corresponds to the projected area. So, on the one hand, the direction in which the detector is facing is relevant for the measured radiant power, and on the other hand, of course, the area that the detector occupies, its field of view, so to speak. The latter is expressed by the so-called solid angle. A solid angle omega is defined by the ratio of an area on a sphere to the square of the radius of the sphere. The solid angle can be understood analogously to the radian. In two-dimensional space, the radian is the ratio of the length of an arc to the radius of the circle. In three-dimensional space, the solid angle is the ratio of a segment of the sphere to the square of the radius of the sphere. If a segment includes the entire sphere surface with an area of 4 pi r square, then a solid angle of 4 pi results. The angle occupies the entire space of the sphere, so to speak. If the area is only half the entire sphere surface, the solid angle is 2 pi. For such an solid angle of 2 pi, the detector would just cover the entire half-space of radiation and detect the entire radiant power of the surface element. The detector would also have to be hemispherical. Note that as long as a considered segment is part of a spherical surface, a solid angle can be defined for any arbitrarily shaped surface according to the given definition of the solid angle. The outline of the surface does not necessarily have to form a circle, as is often suggested in order to specify a solid angle. Thus, the detector does not need a circular sensor, it can also be rectangular or otherwise arbitrarily shaped. It only needs to be part of a spherical surface. For large radii and small surfaces, however, the curvature of the surface is so small that flat surfaces can be used in very good approximation. If one examines the emitted radiant power of the opening of the cavity acting as a blackbody with a detector, then one observes two things. First, the measured radiant power delta P is proportional to the projected area delta AP. Second, the measured radiant power delta P is proportional to the solid angle delta omega the detector covers, as long as small solid angles are considered. The first statement has already been explained. The larger the radiating surface facing the detector, the greater the power. The second statement can also be clearly understood. If two very small detectors are placed directly next to each other, they both register the same power. If one takes both detectors together in thought, which then take up twice the solid angle, then one obviously receives twice the power. Strictly speaking, this applies only as long as the two solid angles are very small and the surface segments are close together, so that they do not differ in the direction of pointing. Otherwise, according to the first statement, one of the detectors would measure a slightly different radiant power. Furthermore, the measured radiant power is of course dependent on the size of the wavelength interval delta lambda, which the filter of the detector allows to pass. A wavelength interval twice as large means that twice as much radiation passes through the filter. The measured power is therefore twice as large. This proportionality between power and wavelength interval only applies to very small wavelength intervals. Thus, the following relationship applies between the measured power of the detector delta P and the projected area, the solid angle, and the wavelength interval. Thus, if the radiant power of a black body is no longer related only to a wavelength interval and to a surface element as with the spectral intensity, but next to the wavelength interval delta lambda to the solid angle delta omega and to the projected area delta AP, then one also obtains a constant quantity. This quantity is called specific spectral intensity or spectral flux. The spectral flux thus represents the radiant power emitted per unit wavelength interval and per unit solid angle and per unit projected area. Applied to our example, this means, no matter at what distance and with what orientation the detector faces the surface element of the black body, the same specific spectral intensity is measured for a certain wavelength interval. Thus, the radiation of a blackbody can also be characterized by the specific spectral intensity. In practice, this quantity has the advantage that one does not need the entire emitted radiation of a surface element to characterize the radiation, as is the case with the spectral intensity. With the spectral flux, only a part of the radiation within a certain solid angle needs to be examined. For the specific spectral intensity, the given formulas apply, which give the specific spectral intensity as a function of the wavelength and as a function of the frequency. We will explain how these formulas are derived in the following. Relationship between spectral intensity and spectral flux. If we look at the formulas for the spectral intensity and the spectral flux, we notice that they obviously differ only by a factor of pi. How this relationship comes about will be explained in the following. First of all, it should be pointed out once again that the spectral flux indicates the spectral intensity per unit solid angle, while the spectral intensity refers to the total spectral intensity of the entire emitted radiation. Since an infinitesimal surface element radiates spherically into half-space, the spectral flux must be added up over the entire half-space to calculate the total spectral intensity. For the spherical half-space, the solid angle is 2 pi. Therefore, shouldn't both quantities differ by 2 pi instead of only by pi? When summing up over the half-space, it must be noted that the spectral flux does not refer to the whole area of the surface element, but only to the projected area. However, both areas are only identical for the special case when the surface element is viewed from the front. For all other cases, the projected area is always smaller. On average, over all solid angles, the projected area is half as small as the area itself. Therefore, the result is not 2 pi, but only pi. In the following, this will be shown mathematically. To compare the spectral intensity with the spectral flux, we have to consider the total radiated power of the blackbody. By definition of spectral intensity, this corresponds directly to the specified power delta Pt. To get the total emitted power from the spectral flux, as spectral intensity per unit solid angle, we have to sum up the radiant power delta P omega over all solid angles. Mathematically, this corresponds to the integration over the entire hemisphere for all solid angles. In this equation, we can cancel out the wavelength interval delta lambda, and we obtain the given relationship. At this point, it already becomes apparent that it does not matter at all whether we use the wavelength form or the frequency form. In the case of the frequency form, the frequency interval would have been cancelled out at this point. Now, a solid angle delta omega must be assigned a direction so that the projected area delta AP can be determined. For this purpose, a segment of a surface delta sigma required for the solid angle to be determined is best described by spherical coordinates. A point on the surface of a sphere is completely defined by specifying two angles. The angle phi is the angle in the xy plane, and the angle theta is the angle to the z-axis. If one now allows both angles to vary within a certain range delta phi and delta theta, the result is a segment delta sigma on the sphere. The area of this segment can be determined on the basis of geometric considerations as follows. According to the definition of the radian, the height of the segment results from the product of radius and the angle delta theta. The width of the segment can also be determined in this way as shown. Finally, the area of the segment results from the product of width and height, and thus is shown. With the definition of a solid angle delta omega as the ratio of the area delta sigma to the square of the radius r, the solid angle is determined as shown. At last, we have to determine the area delta AP projected in the direction of the position vector. This projected area results from the cosine of the angle theta as shown. Putting these two derived formulas into the first equation gives the following relationship. In this equation, we can cancel out the area delta A. We can also simplify the product of sine and cosine by the given term. Now we have to solve the integral. But note that, as explained before, the spectral flux is constant everywhere on the surface of the sphere, and therefore is a constant quantity when integrating. This constant quantity can therefore be written before the integral, just like the factor 1/2. Only the integration over the hemisphere has to be done. This means integrating within the limits of phi from 0 to 2 pi, and within the limits of theta from 0 to pi over 2. First we solve the integral marked in red. The solution of this integral results in 1. Now we solve the last integral. The result of this is 2 pi. So we see that the spectral intensity and spectral flux differ formally only by the factor pi. This is true for the wavelength form as well as for the frequency form. Distribution of the spectral energy density of cavity radiation. The spectral flux makes it possible to draw conclusions about the so-called spectral energy density of cavity radiation. Spectral energy density means the radiant energy contained in the volume of the cavity per unit wavelength interval. For this we again look at a hollow object with a tiny hole. All radiation coming in through the opening is absorbed by the inner walls with every reflection until after a few reflections all radiation is absorbed. The hole is by definition a blackbody that absorbs all incident radiation. However, depending on the temperature of the cavity, the inner walls themselves emit radiation. In thermodynamic equilibrium, the walls absorb as much radiant energy as they emit, so that neither further heating nor cooling of the blackbody occurs. Inside the cavity thus a kind of photon gas is formed. By the way, the derivation of the Stefan-Boltzmann law is based exactly on this idea of photon gas. The radiant energy or energy density in such a cavity can be determined from the blackbody radiation emitted through the opening. For this we consider a surface element delta A at the opening to the cavity. The surface element is thus part of the photon gas. As usual with gases, the photons in the photon gas move in different directions. Half of the radiation thus escapes into free space, where it can be detected. The other half of the photons moves back into the cavity. At any solid angle delta omega, radiation is emitted from the projected area delta AP. The photons moving at the speed of light c cover the distance delta L within the time delta t. Within the time delta t the photons thus occupy the shown volume delta V. The radiant energy delta U in the wavelength interval delta lambda, which is contained in the emitted radiation, can be determined by the spectral flux and the time interval delta t. Thus, the following formula applies for the energy density U as the ratio of energy delta U and volume delta V. In this equation we can cancel out both the projected area and the time interval. The energy density in this form still depends on the wavelength interval and the solid angle. Therefore, the energy density is usually given as spectral energy density, which means energy density per unit wavelength interval. Furthermore, in the case of a volume element, it makes no sense to relate the energy density to a solid angle. After all, the entire volume element is considered with its energy density. Therefore, the energy density must be related to the entire volume. This means to a whole sphere with a solid angle of delta omega equals 4 pi. Therefore, the given relationship exists between the spectral energy density and the spectral flux. Since the spectral flux is in turn clearly related to the spectral intensity, the given relationship is also true. These relationships apply not only to the wavelength form but also to the frequency form. In this case, the spectral energy density then means the energy density per unit frequency interval. The total energy density inside the cavity of a black body would finally be obtained by integrating these equations over the entire wavelength or frequency range from 0 to infinity. This total energy density is only dependent on temperature and is spatially constant throughout the cavity. If the energy density would differ in 2 points, then more energy would be contained in one volume element than in the other. The volume element with the higher energy density would radiate more than the other. However, the photon gas or the entire cavity would then not be in thermodynamic equilibrium. Furthermore, the energy density is not dependent on the volume of the cavity. The spectral distribution of the energy density is solely determined by the temperature. So whether the cavity is small or large is irrelevant for the energy density contained in it. So note that the energy density inside the cavity of a hollow black body depends only on the temperature. We hope you enjoyed the video and found it helpful. Thanks for watching.